Welcome to another video explaining the universe using the particle model. Today's video is part one of nuclear radiation. In particular, we're going to discuss the emission of particles from the nucleus. In the previous 4 videos that I've done on cathode ray tube and canal ray tube, while investigating the deflection of positive ions, the deflection of alpha particles were also explained. This brought up a new topic, the emission and deflection of radiated material. Today we'll talk about emission later. The next one will be on the cloud chamber where we see deflection. Okay, this is a description of nuclear decay. Is a process by which unstable atomic nucleus loses energy by radiation. Unstable nucleus. A material containing unstable nuclei is considered radioactive. 3 of the most common types of decay are alpha decay, beta decay, and gamma decay. Excuse me. It's kind of interesting to note that the names of these are really alphabetical. One of the first ones discovered was the alpha emission, and it probably didn't really know what it was, but had a feeling for it, and so they called it alpha, and then beta emission, which is the electron, and finally gamma emission. So the names really have no significance. The question is, what are they? And this is in part what the discussion is today. Okay, well, it was Enrico Fermi who actually labeled the force that causes this decay. And from this link it states, in nuclear physics and particle physics, the weak interaction, which is often called the weak force or weak nuclear force, is the mechanism of interaction between some atomic particles that is responsible for the radioactive decay of atoms. They call it a force, but they never clearly say what it is. It's a mechanism of interaction between particles. Actually, that's not really a bad one, but it doesn't. When we look for a force, we're looking for some sort of definition of a thing that's pushing or pulling and moving something. And no, this is just an interaction. Well, the particle model has no weak nuclear force. We have really forces generated from the G1 particle, G1 gravity, and G2 particle, G2 gravity, but no other force. And the standard model does not explain the source of the weak nuclear force. What is it? How does it break up a nucleus? Well, in a way they had what I consider the answer, but they don't clarify it that way. They claim it's an unstable nucleus with interaction between particles. I just regroup their own answer. The particle model then suggests that some parts of the nucleus are not properly aligned with the rest of the nucleus, hence unstable. Since atoms at normal temperature vibrate, they will hit each other. This is an interaction, releasing electrons and gamma rays, which helps to stabilize the nucleus. Alpha rays then are emitted when the imbalance nucleus converts to a balanced nucleus, and in particular, and in any number of examples, uranium-238 changes to thorium-234. It's a failure of the nuclear binding force, according to the particle. It's a failure of the nuclear binding force, which in the particle model is G2 gravity, to hold the nucleus together because it's unstable. So let's start with the alpha particle. The alpha particle is identical to the nucleus of a helium-4 atom, which consists of 2 protons and 2 neutrons. It has a charge of +2 and a mass of 4 units. For example, as I stated earlier, uranium-238 decays to thorium-234. How do they know it's identical to a helium-4 atom? Because 238 decays to 234, losing 4 units, and the helium-4 nucleus has exactly 4 units. Just a matter of simple deduction. So this is the typical nuclear equation here of the uranium decaying to thorium and an alpha particle. Uranium-238 to thorium-234. Uranium has 92 protons, thorium has 90 protons, helium has a mass of 4 units, which is the combination of 2 protons and 2 neutrons, but this shows it's two protons. And in the process, the uranium loses 4 units. One other side comment is that if helium-4 is unstable, it could decay to helium-3. And I'll talk about that a bit later. Okay, the alpha particle, though, in the particle model. The alpha particle would consist of 4 nucleons which are labeled N1. N1 is the equivalent of 1 proton or 1 neutron that exists in level 1, where the N1 has no charge, where the proton supposedly has a positive charge. One of the interesting things in the particle model is that the alpha particle can gain any number of G1 orbitals, that is, electrons around the nucleus or the G1 orbitals around the N1 nucleus, as long as the G2 gravity can hold them together. It can gain 1, it can gain 2, it can gain 3. Possibly 3 isn't a stable atom and decays quickly to 2. Not sure what it really has, but the particle model doesn't exclude how many G1 orbitals an atom can have, just that it has it for a period of time while unstable and then loses some to get to a stable configuration. Okay, so let's talk about beta emission. This is the second picture. Here's a nucleus emitting an electron. That's a negative electron is a beta, although they have symbols, beta plus and beta minus. This is really a beta minus. And it emits an electron. What this subset indicates is that inside there's a neutron that is actually emitting the electron, and the neutron then converts to a proton because it's lost a negative charge, so it becomes positive. And this is what they expect to see. So, but this down here is actually an anti-neutrino. Now, the nu, which is the Greek letter nu here, is the symbol for the neutrino. This neutrino is associated with an electron. That's what the E means. And the bar over it says it's an anti-neutrino. No bar, a neutrino. With a bar, it's an anti-neutrino. And they had to add this, and we're going to explain that here momentarily. The neutrino saves special relativity. Page 4 of Storm and Physics by Riccardo Carezani. This is his book, Storm and Physics. This quote is on page 54 of his book. You can get that on the internet, I believe, if there's any left. But Carezani states, normally in science, experimental research starts when a theory proposes something positive. Neutrino research is reversed. It starts with an evident failure. We need to prove neutrinos exist, or special relativity is wrong and fails to explain energy momentum conservation in beta decay. In other words, when they added up the energy momentum of the neutron, the proton, and the electron, came up short. Physics textbook really explains it a different way, or similar but different. The neutrino is a particle emitted in beta decay that was unanticipated, and it is of fundamental importance. I didn't find what the fundamental importance was. Maybe it's the balancing. The neutrino was not even proposed in theory until more than 20 years after beta decay. So they had beta decay, they had the imbalance. After 20 years, they give up and say, okay, there must be a neutrino. Neutrinos are so difficult to detect that the first direct evidence of them was not obtained until 53. They claimed they did detect them in 53. Well, David, my son, helped Karazani with his book and became convinced that Karazani was right. I will ask David to tell you about his experience trying to prove the neutrino, that the neutrino was invented to explain the missing mass energy. If you ever looked at, in fact, I had a video on this, didn't put down the reference here, where I explain how you can take the mass energy and you use E equals mc squared to convert the mass of the neutron into energy, and you do the same thing over here, your masses of these two to energy, and the numbers don't add up. David went through quite an experience trying to prove the neutrino was invented, not discovered, invented. Okay, but in the particle model, beta emission is really important. Beta emission generates the G1 particle field. This is a G1 particle field, and I mentioned this is a new drawing by David, and I changed it. I put stars here in orange, showing that their stars are emitting beta particles, and beta particles are electrons, and in the particle model, G1s are electrons with no charge. G1s are emitted from 70 sextillion stars. That's an estimate. I don't think they literally counted. That's how many they estimate is that they get from the observable universe, meaning there's probably more. So you've got millions and millions of stars emitting them all around us, and all of the stars, they emit G1 particles in all directions, and many of them reach the Earth, setting up G1 gravity around the Earth. This beta emission is what generates the G1 particle field. Okay, there is not only helium-4, but there's helium-3, and this is a diagram here of helium-3 with 2 protons and a neutron, 2 electrons, and this is helium-4, 2 protons, 2 neutrons, and 2 electrons. The natural abundance of helium-4 accounts for 99.999866% of all the helium atoms on the Earth. Helium-3 is extremely rare and accounts for only this, which is the difference from 100% of the Earth's helium. Well, what's the source of helium-3? Is it the alpha particle? Or maybe it's an unstable alpha particle that is not quite balanced, that loses a neutron, and that's why this occurs. That's a conjecture on my part, just guessing what might have happened. And in fact, you could have free alpha and beta particles in space, and they could combine. An alpha particle could be flying through space and meet up with 1 or 2 beta particles, which this is like a nucleus, and these are like electrons, and form a helium-4 atom. Probably easy to capture 1, harder to capture 2 and get a stable configuration, but over time could also do that. It does not easily happen, but with the particle model, it says it could. The standard model doesn't talk about it being generated in space. Maybe it does. I didn't search for that, but particle model does not exclude that possibility. So on to gamma radiation or emission by the standard model. Gamma ray bursts. Gamma ray bursts are short-lived bursts of gamma ray light, the most energetic form of light, lasting anywhere from a few milliseconds to several minutes. Gamma ray bursts shine hundreds of times brighter than typical supernova, hundreds of times brighter, and about 1,000,000 trillion times as bright as the sun. Bright, they're very strong. When a gamma ray burst erupts, it is briefly the brightest source in the cosmic gamma ray, in a source of cosmic gamma ray photons in the observable universe. Getting tongue-tied. But that's the same video, the same thing had a video in it. This from NASA, and it runs for a period of time and captures 500 gamma ray bursts. This is a gamma ray burst. This is a satellite that had a gamma ray detector on it. The satellite was actually looking for other countries working on nuclear processes. Yes, spy satellite. At any rate, you can see this is years 2006, but we're already into this. It actually starts in 2004, goes to 2010, and at this point, at 2006, it has already detected 100 gamma ray bursts over 2 or 3 years. And by the time you get to the end, and these gamma ray bursts keep popping up, and you have the difference. These are the intensity of your normal light from distant stars and galaxies. Presumably this is our sun, and this is the gamma. You can see the intensity, the difference in the intensity. Short-lived, high intensity. Well, gamma ray emissions in terms of the particle model are streams of G1 particles in a repetitive pattern. Somehow the nucleus, and I find it hard to believe it's one nucleus generating a gamma ray, because in the particle model, to back up for a moment, the standard model says it's an electromagnetic radiation. That's what it is, but it comes from the nucleus or many nucleus, and so you get peaks rapidly from a source somewhere in space, presumably from a much larger group of nuclei, each one emitting these things and moving at speed c. Streams of G1 particles with a repetitive pattern. The intensity is determined by the number of G1s at the peak. If you have very few here, it's not very intense. If you have a lot of G1 particles, it's very intense. You can imagine if you have a gamma ray detector, when this peak hits it and it has a large number of G1 particles hitting the detector, you're going to get a strong signal at that detector. By the way, they can lose their intensity as they travel over, because these are coming from millions of light years away. When you have an incidental collision between the G1 particle field that I talked about before and this stream, you could incidentally lose a few of these particles, and the intensity decreases over distance. The duration is determined by the number of peaks emitted. I took the time to calculate how many peaks are in a 1 millisecond burst. 10 to the 17th peaks. That's why I don't think one nucleus does that. It has to be millions of easily millions of them, more than that, even for a 1 millisecond burst. It requires that many to get that short of a burst. And so the duration is short because whatever source has so many of these nuclei to generate those peaks, it ends quickly. Okay, finally, X-rays. X-rays are not nuclear-based source. Gamma rays come from the nucleus. X-rays are normal electromagnetic radiation, comes from outside of the nucleus. And this is a picture of an X-ray with its intensity. This is visible light that we see from normal stars and galaxies. This particular view compares the Perseus cluster here as seen with an X-ray detector where the view of mostly is this is mostly hot gas, to the visible light from the stars of individual galaxies. Kind of shows the intensity. Gamma rays are much brighter than this, and clearly brighter than that. The interesting thing about X-rays and gamma rays that in the spectrum, they occur at the same place. A very high frequency. This is the X-ray, which is, again, emitted from atoms, but it's from G1 particles outside the nucleus, whereas the gamma rays are emitted from the nucleus, and they're in the same area of the spectrum. So this electromagnetic spectrum is electromagnetic. This looks electromagnetic, but it's generated in a different source. Okay, next time, part 2, the cloud chamber. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time. We'll explain more of the universe using the particle model. Thank you for your attention.